Okay, so let us begin. This video will be about using the DwSIM software. It is used in many engineering applications, but we're going to focus on the thermodynamic applications. So today we're going to be simulating the Carnot cycle. These are heat engines that convert heat to work. So first, in order to install the software, we're going to go to a browser. I'm going to use Brave, and you just search DwSIM. You may land to something like this, so we just go to download, and we scroll up to Windows 64-bit. So if you're in Windows, you download the installer package. Do not install portable package. Do not install this. Let's say there's some problems with that, like navigating and all that stuff. You only install this if you know you're going to supply to other people. For example, cyber the people who run cybers may use this package so that they can install to other people's computers. But since you're installing directly into your computer, then download this one. So we download it. Depending on your browser settings, it may show if it's going to download. For example, mine, it always asks for where to be installed. Let me just set it to downloads and install. So we're not going to wait for all this time because we already have the package. What I'm going to show you is that once it has finished downloading, you may go to where you have installed it, the folder which you have installed the package. Let me go and search mine. Let me see, it is right over here. So mine is over here. I know I've installed it a long time ago. So what you're going to do, once you have the setup, you double click it, left click, double left click to set it up. Now I already have it, so I'm just going to show you what you can do to navigate since I already have the application. But let us see. I'm going to show you. Let me cancel this one since I do not need it. So most of the time, if you're on Windows, it will ask for administrator privileges. So we click yes and let the setup begin. Select English. Okay, I can say yes and let it run. Click next. you click I agree, then next, leave it as it is. So next, this is a folder, usually I just let it to be default. So next, install, and it's going to install everything that it's going to need. So this one might take a while for it to install. Once it is completed, we're going to click next, and we just finish. So from there, depending on where you have, how you have set up your computer, you may go to Windows and search for DwSIM, and it will show you. So I'm going to use this cross-platform UI. I think that's like the modern type, the modern one. Yeah, so we are going to use that, but also the other one you can use it, but I find the UI, I find the user interface to be old, to be, yeah, it gives the old vibes. So you'll be given such a launcher. So what you're going to do is click new on the processing modeling, you click create new, and it will give you this setup wizard. So you click next, and since you're dealing with Carnot, you're going to deal with water and steam. So what you're going to do, you're just going to choose research for water, press enter, and then click this. Once you've seen there's a tick, then you can continue to next. You're only going to deal with the water. In this case, water will be our working fluid. So next, what you're going to do is you're going to go to I want to select or use a specific property package. This is because I find that, as you can see, there are a lot of property packages, but I want to be as close as the examinations, that is for the universities in Kenya examinations. They're going to be using the steam tables, so we're going to use this property package, steam tables. I find this to be, it would be accurate if you compute the enthalpy in other properties by hand. I see it be very close, other than Coolprop or Paying Robinson's property packages. So we choose the steam tables IAPWS IF97 package, and we click next. Now we can change the simulation. Let us change the name to Carnot cycle. Carnot cycle. And in the system of units, SI are the default. Here you can find in the temperature in Kelvin, all the stuff. So what you're going to do, you're going to use C5. The C5 is commonly used for like everyday properties, for example, pressure in bars, temperature in degrees Celsius, but in the mass flow rate will be in kgs per hour. We're going to just see about that. So after I click that, you click finish. Now you have something like this. What you're going to do, you're going to add a material stream. Just drag it, click and drag onto this template, and then double click to make it into view. Now click it, and you'll see something pop up on the side. You can change the name to be water inlet, and we can deal with some properties over here. As you can see, specify variables is temperature and pressure, temperatures in degrees, pressures in bars, specific enthalpy in kilojoules per kg, and all that stuff. So we're going to focus on the temperature and pressure. Since you're dealing with Carnot, I'm going to specify a temperature of 400 degrees Celsius. I think that is too much. Let's say 260 or 250. Let's just say 250 degrees Celsius at a pressure of 30 bars. And then so make sure it is temperature and pressure, because that is what of input, that is what you're going to be using. And then you're going to drop to see, as you can see, the mass flow rate is in kgs per hour. You just divide this by 3600 to find the kgs per second. So this it's an equivalent of 1 kilogram per second. We're just going to say leave it the way as it is and accept and update. So once it has calculated, it will turn blue, and yeah, we are done. So from there, now we need an expander. An expander, that will be our turbine. So mostly what we're going to do is, usually in Carnot, what we care about is the temperature difference, temperature of the inside and the outside. And we do not usually need a pump for that, because the working fluid, the enthalpy of the working fluid is not taken into consideration for the efficiencies. Mind you, this is like the most efficient heat engine you can ever get. Nothing can be better than a Carnot engine, and therefore Carnot engine only focuses on the inlet temperature and the outlet temperature. You can see, you're going to find it can be used in finding the efficiency of a Carnot engine. So you've already, the temperature is 250 degrees, the pressure is at 30 bars. So the next thing we need to do is just input into a turbine. You can find a turbine in a pressure changer, since it expands. So we click it and then we drag it. So depending on the DwSIM version that you've selected, it will depend. So mine automatically connects the inputs and the outputs. So we double click to make everything into view, and as you can see here, this is now expander. We click it and you find its properties on the left. So the inlet is the water inlet, outlet is this, and the energy stream. This is now going to give you, as you can see, it points outside. This gives you the energy output of the turbine. So let's go to the properties and change the name to turbine. And the calculation mode will be the outlet pressure, because you are going to specify the outlet pressure. So we'll go to the outlet pressure and let it to be around 10 bars, and that's it. That's the only thing. Oh yeah, and everything here to be 100%, because you're dealing with an ideal Carnot engine, and that's it. Make sure the thermodynamic path is adiabatic. Adiabatic means that, okay, as you can see, there is adiabatic and polytropic. So adiabatic means there's no heat outside and heat exchange between the turbine and the surrounding. And in such a software, it treats a turbine as one component. The fans, the shaft, everything is treated as one component, and is actually simpler to calculate because it is discrete. It takes just chunks, specific chunks. For in our case, we have just one turbine, and we do not know the stages inside the turbine, so we're going to use adiabatic. But for larger power plants, more complex power plants, the turbine is usually comprised of many stages, and every stage has its own entropy. There will be some loss due to friction, all that stuff, and you cannot use adiabatic since it will be inaccurate. For such cases where you need very accurate results, you're going to use polytropic thermodynamic path. So in our case, we're going to use adiabatic, and you want it to be 100%. That means there's no heat gain and loss inside the turbine. You want just to expand the pressure isentropically. So once you're done with that, I can come here and change this to be the water outlet. And once you've done that, then we can click run. You can either press F5, the function key F5, or here you just click solve flowsheet. Once it is solved, as you can see here, it will turn blue, meaning it has been calculated successfully. So sometimes it may tell you that, let me change this thing from the water inlet, let me change it to be around, let's say 120 degrees, and see what happens. As you can see, there's something over here. It says the turbine liquid phase detected in expander inlet, and as you can see also, the energy output has reduced drastically. So we make sure the combination of the temperature and the pressure always puts the vapor fraction of this to be 1, to be purely vapor, because that's what you want. So you can go to the results and try to see the vapor fraction of this inlet. So as you can see here, the vapor is 0, liquid is 1. So at 30 bars at a temperature of 120 degrees, the liquid is still, the water is still in the liquid phase, and that is bad. You want it to be in vapor. As you can see, the vapor phase mole fraction is 0, which means it's purely liquid, but you want it to be vapor. So what you can do is either you change the properties of the pressure, either you reduce the pressure or increase the temperature. You want to make sure that it is always superheated or something close, something above the saturated vapor point. You want it to be a little bit higher so that it can be superheated. So I'm going to return it back to 250 degrees and then play it. As you can see, calculate successfully with no warnings, and we can go to the results and see that the vapor phase mole fraction is 1. The vapor is 1. It's purely vapor and gives you 213.39 kilowatts. So this is the energy output of the turbine. But what we care about is the efficiency. So what you're going to do is we can I've told you for the Carnot engine we use the temperature, the change in temperature, or the temperature for the inlet and the outlet, or the hot and the cold one, and use that for the efficiency. So in order to see the temperature, either you click the individual inlet and outlet, you click it and go to the results, see the stream temperature is 250 degrees, and the outlet, you click it and you go to the results. Sometimes it might hide itself, so click this and go to the results, and you can see the steam temperature is at 179.86 degrees Celsius. Okay, so what you can do, so that you cannot just be doing this, you can go to the setup and go to the flow sheet settings. Setup flow sheet settings on your top left. Click it and it will give you such a window. So from here you may scroll down and click I want to see the temperature and the pressure. So this is going to displays the real-time properties, and I just remembered that Carnot uses temperature in Kelvin, so we need to go to the SI units or SI engineering, whichever one that has Kelvin. Once you're done, we click this. Do not know why it has not changed the temperature. Let me try to run it. Okay, so apparently it will not change it. Let's try SI units. So the SI units has temperature in Kelvin. The SI engineering has temperature in Celsius and other stuff. So we need the temperature in Kelvin. You use SI units specifically. So as you can see here, we have a pressure in the inlet temperature is 523.15 Kelvin, and the outlet of 453.04 Kelvin. And here it is in pascals, so you can see it's at 3 megapascals, that's 3 million pascals, and here the output is 1 pascals. We said that you want it to be at 10 bars, that's 1 million pascals. So now in order to find the efficiency, we cannot go directly. We need to use the formula to find the efficiency of a Carnot engine, that is 1 minus temperature of the cold side divided by the temperature of the hot side. So we need to go to the spreadsheet and write that formula. So first, what do we need? We need the temperature of the cold side. So what I'm going to write, double click this in the spreadsheet and write the cold, or let's say just T underscore. Okay, so we're going to put temperature cold over here, click enter, then we double click this, it will be temperature hot side, click enter. Now we need to import the values. So under this, or I just put on one in the row. I think the row side becomes neat. Double click this to delete it, backspace, enter, come over here, double click hot side. I think we put it in the rows, it will be much beautiful or more neat. So we come here and we need to, what I meant is click it over like here, select a cell, right click it and say import data from flow sheet object. Click that. So what do we want to import? We want to import a material stream. The water inlet and the water outlet were material streams, so we're going to select material stream, which is over here, letter M. Once you click it, you're going to see the material streams. There's inlet and outlet. So for the T cold is the outlet. Remember, as when vapor is expanded, its temperature drops since the pressure drops, using the Boyle's law or something like that. So I'm going to click the outlet, click the temperature, and we click it in Kelvin. I see we should not, we could have, it's either we could have changed the units or we just click the units that we want, it will just take it. So we want it in Kelvin, so it's a feature in this software. Click OK, and this is going to be the temperature. So as you can see, you cannot see it very well, so what we're going to do is that we expand it, and now we can see the temperature in Kelvin. So the T hot is the one for the inlet, so we do the same thing. Select the cell, right click, import data from flowsheet, go to the material streams, letter M, material streams, inlet, temperature in Kelvin. Okay, and as you can see, it is 523.15 Kelvin. So the formula is 1 minus T cold over T hot, or for those people who they know that it is T hot minus T cold divided by T hot. It's just the same thing as 1 minus T cold over T hot. So what we're going to do, so the formula to find the efficiency, double click efficiency in percentage, enter. So efficiency percentage, let us resize the column to fit everything. It will be equals to, into brackets, 1 minus, or rather 1, it will be equals to 1 minus, into bracket. This is just to make sure that first we are going to deal with the fraction T cold divided by T hot, then we subtract the answer from 1. This is to avoid confusion. So it will be T hot. So what is that? I mean T cold. Or T cold is in the, it is in this cell B1. So it will be B, capital B 1 divided by B, capital B 3 equal sign. So you're going to get this answer, but you wanted to find it in percentage. So what you're going to do is enclose everything in brackets. Either use square brackets to distinguish from the others, or just use the same parentheses multiplied by 100. Now this seems something is wrong. Don't know what happened. I don't know why it's giving us a negative sign. Should give us something that makes sense. Okay, what I'm going to do is, this is going to be our efficiency, because I don't know why it is giving that. I thought it would give us 13%, and under it double click and write efficiency in percentage. And now over here I'm going to reference this cell, so it's going to be equal to B6 multiplied by 100. Yeah, 13.4%. So for this configuration, as you can see here, the maximum percentage you can ever get is for 13.4%. So how can we improve this? Go to the flow sheet. How can we improve this? One, it's either we increase the inlet temperature. Yeah, you can either do that. So in order to know, so that you cannot go back and forth trying to see how the efficiency has updated, what you're going to do is go to the objects, and then we say add new linked spreadsheet table. We have find something like this. We double click it and we say the cell range will be between, so we need to go back here. We see if you want from A to B. So what are we going to do? We're going to say from A, capital A1 colon up to B8, capital B8, and that was going to reference all of this A1, B8. As you can see, this is exactly what it shows up. So if you do not know what to check, so you can just click all of this, then we copy this thing, select this, copy, or just write it again over here. Once you've done that, we click enter. Go to the flow sheet and click enter. As you can see here, it has populated everything. Double click so that everything can be in view. And as you can see here, we have the temperature cold, which is just this one, correct to, I think this is 15 decimal places. This is a double. This is a type of I think these are types of format specifiers, integers. This is a double. This is a temperature hot, the inlet one, the efficiency, and the efficiency in percentages. In percentage, that's that in. So what I say, we can increase the efficiency by increasing the inlet temperature. So we click this. This is our inlet here. We go to the properties and increase it to, let's say, 360 degrees. And as you can see here, once you click enter, it may depend. Once I've clicked enter, it has updated everything, or just to make sure, run it again. As you can see, the temperature has increased from 500 to 633. The temperature cold has also increased, but this is because it is taking the pressure. It's taking the sensor said we wanted to cool it to a pressure of 10 bars. It's taking all that stuff and finding the temperature and pressure for that, like the temperature drop, the enthalpy. It's taking the change in enthalpy with respect to the steam tables. So as you can see here, it has also increased from, I don't remember, equal what it was, but it has increased to 490, but the overall efficiency has increased from 13% to 22%. This is actually not that good. The efficiency is not that good. Usually for steam turbines, the temperature is usually, the efficiency is usually at 30 to 40%. So here we can just see that that pressure here is just so small. What you can do is go to the outlet and you say you want it, go to the turbine. That's why we want to, when we want to change the temperature or the pressure. So I find doing something like this to be hectic. So what we're going to do, we're just going to change it into bars. So go to flow sheet and we go to SI engineering or C5, whichever is good. Let's change it. So as you can see here, since we selected the temperature in the spreadsheet to be in Kelvin, it will always be in Kelvin, and that is very good. But for quick the visual how you perceive it is actually much better if you see it in Celsius and in bars, since they're not large numbers, but you can clearly understand what is going on. So as you can see here, the water outlet is at 217. Remember, it was 178 degrees Celsius. So what you can do is either we can decrease the bars, the pressure, from 10 bars to let's say 1 bar. As you can see, I have run it again so that the properties can populate over here in SI engineering units. So we want it to go to up to, let's say, 5 bars, and we click run. So once I've done that, you can see the temperature has dropped, but this has not changed. So what you can do is try to run it again. Yes, and as you can see it has changed. The efficiency has increased to 32%, and I think this is very good. So I think this is very good. So this is the basics for a Carnot engine. So Carnot engine is like the master of all engines. There's no such engine with this configuration where the inlet temperature is 360 degrees and the pressure is 30 bars that will give you more than 32.877%. No other engine ever. If it does, then that engine is violating the thermodynamic laws, the laws of thermodynamics. And we use this as a reference to see the theoretical maximum efficiency of a heat engine. And it seems as if I've not explained what a heat engine is. Let me say this. To convert work to heat is very easy. Actually, it always does that. Maybe through friction, some inefficiencies, some entropy. So you can convert work to heat very easily. Rubbing your hands, a brake pad in the car, something rotating, the shaft that are friction. Mostly friction is the culprit, but you can do that automatically. But not converting heat to work, that's where we cannot convert heat to work directly. We need a heat engine. So that's where Carnot engines come in, Rankine engines come in, and all those machines and all those engines. They try to convert heat to work, and there's that kind of balance, the efficiency, where how much heat are you converting to useful work. That's what you're using as the efficiency. So in this case, 32.877% of the heat, of the total heat, has been converted to work. And you can see that work given is at 407.69 kilowatts. So you can even compare, you can multiply this, you can find the 100% of this and find the inlet, because the heat energy is coming from the water inlet. So you can try to find all that energy of the water inlet, multiply by that 7.877%, that 2.877%, to get 407.69 kilowatts. Is what you're going to give. And I think this is the simplest engine in terms of some properties. This is the maximum. So what you're going to do next, in the next video, it will be finding the using the same properties: inlet temperature of 360 degrees, inlet pressure of 30 bars. We're going to try to do that now with ideal Rankine and actual Rankine cycle. So thank you for watching this. If you have any questions, I'm going to send this video to the YouTube, so write them in the comments. So thank you, and that is it. Happy New Year.